So one thing to take into account is that chemical properties of atoms are determined by the number of protons and the arrangement of electrons around the nucleus. Remember that the number of protons is determinant of the type of atom that we have. So for example, all neon atoms are going to have 10 protons. And electron interaction is something that we're going to discuss a little bit later on, because the electron interaction will indicate to us how different atoms bond with each other, how they share electrons, how they might donate electrons. It's basically how chemical bonds are formed between different atoms. We define element as a pure substance in which all atoms have the same atomic number. However, that does not necessarily mean that they contain the same number of neutrons. Remember that the number of protons is based off of the atomic number. So if an element has the same atomic number, it means it's going to have the same number of protons throughout. Again, neon is going to have 10 protons. It may or may not necessarily have 10 neutrons. That is going to be because we have these things that are called isotopes. And isotopes of the same element have the same number of protons, but a different number of neutrons. So isotopes will be of the same element. Remember that isotopes contain the same number of protons, so you may have, in this instance, multiple isotopes of silicon. In this case, we have 3 different isotopes. We would use silicon 28 to describe the first isotope. Remember, the 28 is the mass number, that's protons plus neutrons. Silicon 29 to describe the second number, and silicon 30 to describe the third number. All 3 of these have 14 protons, but because the mass numbers are different and the atomic numbers are the same, that is indicative of them all having different number of neutrons. Most elements have a variety of different isotopes. Not all of them will have 3. Some will have 2, some will have 1, some will have 7 or 8, depending upon the element that we're looking at. There really isn't necessarily a way we can go through and predict that. There are 286 isotopes that occur naturally, and if you think about it, there's roughly 92 elements on the periodic table that occur naturally. So, roughly 3-ish isotopes per element on the periodic table. Again, that's not evenly distributed. That is just a number that's distributed throughout. I also want you to take a look at the percentages in the top right-hand corner there. Not all isotopes appear in the same percentage. That is, because silicon has 3 isotopes, it doesn't mean that each isotope occurs 33.3% of the time. In this example, silicon 28 appears 92.2% of the time, significantly more than that of silicon 29 and that of silicon 30. So the distribution of isotopes is different, and that distribution of isotopes leads us to what is called the average atomic mass or molecular weight or atomic weight. There's a variety of ways to describe it, and that is the decimalized number that you see on the periodic table. So go ahead and take a look at the periodic table and look at silicon. Silicon's average atomic mass is 28.09. All right, that is what is known as a weighted average of all 3 of those individual isotopes. I know I'm getting a little bit ahead of myself, but I want you to keep in mind that that number is something that's going to be very important to us as chemists as we continue to move forward in this course. So take a look at all of the different isotopes and the different atomic masses that are listed here. Hydrogen has 3 isotopes, but the most abundant one is that very first one. 99.985% of all hydrogen is that first isotope, where we just have 1 proton and no neutrons. And then you have a second and third isotope below. Most of helium is helium-4. That is that there are 2 protons and 2 neutrons. I'm moving forward to lithium. Most of lithium is lithium-7 with 3 protons and 4 neutrons. There's a little bit of lithium-6 with 3 protons and 3 neutrons. And you can see as you go through, there's a variety of different isotopes that apply to each individual element that is on the periodic table. Some have 1, some have 2, some have 3. As you would continue further up the periodic table, you tend to find that there are more relative isotopes. I also want you to notice that the abundances are different for each individual isotope within each element as well. They're not all 33% or 50% or 100%. Many of them have a variety of different weights that are associated with them. Again, different isotopes mean that different atoms of the same element can have different masses, right? If we add in more neutrons, we end up finding that those specific isotopes have a greater mass, right? Hydrogen's mass number for its most abundant isotope is 1, but for its second most abundant isotope, it's 2. Again, the mass number of that being 2. And then hydrogen also has an isotope with a mass number of 3. So how do we get the mass of a sample of an element? If I were to take a chunk of an element, it's very unlikely that I get just one individual isotope of that element. So how do I take the mass of that particular element? And what we do is we take what is called a weighted average. So I want to take a step back from chemistry for just a moment and want you to think about the term weighted average. Many classes that you've taken either in college or in high school had a weighted average associated with them. And I'll give you an example from my classes that I teach at a local high school. In one of my classes at a local high school, tests are worth 65% of their grade, while labs are worth 20% and homework is worth 15%. So it would stand to say that tests and exams are worth significantly more of their average, because it's worth 65% of their grade, than that of labs and homeworks. So that means that their grade is going to be more weighted towards that 65% than it would be the 20 and the 15. And it's very similar to these isotopes and these weighted averages that you're going to find on the periodic table, is that you're going to find that the average atomic mass, that is that decimalized number that's on the periodic table, you're going to find that that's much closer to one of these isotopes that has a higher abundance associated with it. So the atomic mass that I've been referring to is the calculated average for the mass of isotopes of an element that's on the periodic table. Again, it's that decimalized number. So if I look at hydrogen, it's 1.008. If I look at lithium, it's 6.94. Beryllium, 9.012. All of those are weighted averages that you're going to find present on the periodic table. Now, how do I calculate that? Is based off of this information here. You simply take the mass of each isotope and multiply it by the decimalized form of the percentage, and then take the sum of those values. So for example, I'm looking at lithium here. Lithium has two isotopes, one with a mass of 6.015 AMU, and we'll talk about what that means in a moment, and then one that is 7.016 AMU. So there's two isotopes that are here. I take each individual weight and I multiply it by the percentage. Now remember that percentages in decimalized form have been divided by 100. So notice I'm not taking 6.015 AMU and multiplying it by 7.42, but rather I'm multiplying it by 0.0742. You divide that percentage by 100 to get the decimalized form of the percentage. I do the same thing for the second isotope. I take 7.016 AMU and multiply that by 0.9258, and what I get is 6.50 AMU and 0.446 AMU respectively for each multiplication I did. I add those two together and I get 6.94, which is exactly what I find on the periodic table. So given any set of isotopes and their weights, you can very easily determine what the average atomic mass is going to be on the periodic table, or the atomic mass as it's listed here. Now again, take a look at the decimalized number that's on the periodic table for lithium. This is the atomic mass and molar mass. It should be the exact same value as you go through and calculate. And we're going to use this number quite extensively as we work through some materials a little bit later on. So it's very important that you know how to calculate this, but even more importantly, know how to utilize it a little bit later on. A couple things to think about before we go through and do more calculations with this. Remember that this is an average. It's a little bit different than taking a normal average where we just take two numbers, add them together, and divide by 2. A weighted average is a little bit more different than that. And it's still an average just the same. So what that means is that if I take the average of two values, regardless of whether it is a normal average or a weighted average, the numerical value should be in between the highest and lowest values. So if I take a look at that 6.94, I find that it is between 6.015 and 7.016. In addition to that, I can take a look at the percentage and get a better idea of what isotope's mass it should be closer to. Most of the isotopes in a sample of lithium are lithium-7. So what that means is that my numerical value for the average atomic mass should be closer to 7 than it should be to 6, because the percentage of isotopes that are 7 are greater than that of 6 significantly, right? 92.58% of a sample of lithium is lithium-7. So that tells me that the average should be much closer to 7 than it should be to that of 6, all right? So I have a sample problem for you here. It's exactly the same as what we just did. You just simply need to take the mass and the abundance and multiply them together for each of these, and then add them together when you're done. So before we even start this problem, I want us to get a good idea of what we're looking at here, because if we have a rough idea of what number we're looking at, it's going to make it so much easier for us to go through and calculate it a little bit later on. We have a relative mass of chlorine 35, and it gives us the AMU of 34.97. If you want to know why it's not 35 exactly, you can ask me later. And its abundance is 75.53%. And the relative mass of chlorine 37 is 36.97 AMU, and its abundance is 24.47. What is the atomic mass of chlorine? First off, I know it has to be somewhere roughly between 35 and 37, because those are the highest and lowest values that are given. In addition to that, I'm venturing that it's going to be closer to 35 than 37 because 75% of the mass of chlorine is going to be that isotope with the mass of 35, as opposed to the one with the mass of 37, which is only 25%. So I'd like you to take a moment, pause the video, go through, calculate that average atomic mass, and see if we get what we've predicted. I'll be back in just a moment. So here's the math done for you. Atomic mass here, 34.97 AMU. We're multiplying it by the decimalized form of that percentage, 0.7553. And then I'm going to add to that 36.97 times 0.2447. Sometimes it's best to do this separate from one another rather than doing them combined into one type of problem, but you can do it however you feel the most comfortable. Regardless of what happens, when I add them together, I end up with 35.46 AMU. And if I look at the periodic table, that's roughly I usually use 35.45 personally, but it's roughly the same as what I would have on my periodic table. And first off, I need to check and see, is it between 35 and 37? Yes, tick 1, done. Is it closer to 35 than 37? Yes, tick 2, done. So, that being said, you should be able to very easily go through and solve these problems. Just make sure that you take the percentage and put it in the decimalized form. That is the number one area where I see the most mistakes from my students. So again, some tips and tricks. If you have more than 2 isotopes, you'll need to repeat this procedure with 3 or 4 calculations rather than 2. So don't just go through and do 2 calculations. If you see 3 isotopes, you need to do 3 calculations and then add them together. Watch your significant figures, and then remember, it has to be an average. It has to be in between the highest and lowest values, just like we discussed, and we can make a prediction as to which isotope it's going to be closest to based on the percentages that are given. You also need to include your units, and for right now, you can include AMU or grams per mole. We'll talk about the latter in the future, but either of those are perfectly acceptable units for this particular calculation. All right, so I've got one more practice problem here associated with calculating average atomic mass. So let's take a look and read through this quickly. It says a sample of a chemical element has 3 isotopes, one with a mass of 23.985 AMU and an abundance of 78.70%, another with a mass of 24.986 AMU and an abundance of 10.13, and one more with a mass of 25.983 AMU, and with an abundance of 11.17, and what is the average atomic mass of the sample. So in this instance, we have 3 individual isotopes that we need to take the average atomic mass of, but we follow the exact same rules that we did before. We have use the pen, Jude. That's one of our isotopes, another one of our isotopes, and a third of our isotopes. So all we need to do is take the individual mass of the isotope and multiply it by the abundance. So 23.985 times, and again, that needs to be in decimal form, so 0.7870 plus 24.986 times 0.1013 plus, I'm going to write this down here at the bottom, 25.983 times 0.1171. Now, when I add all of those together, it should be somewhere between roughly 24 and 26. And what I notice here is that the highest abundance isotope is that's closest to 24. So when I go through and calculate, it should be closer to 24. So let's go through, do some math, and see what we come up with. My mistake, I did realize that this should be 0.1117, but what I end up with is an average atomic mass of 24.31 AMU. And it asks us to identify the element from the sample based off of the periodic table. So go and take a look at the average atomic mass. You're going to find that that is closest to that of magnesium. All right. So again, take your time. It's not that difficult to do. Just again, make sure that you read the question very carefully, identify the information, the problem that you have, and take some time and go through and solve for it.